Okay, welcome to the MNGRL Lab. That is its name, and for a very good reason, MNGRL, yeah. So it's MNGRL, and it basically stands for the Mid-Atlantic Nobel Gas Research Lab. But it's very well named because we actually study lunar samples in here. So and it was, up until recently, it was just 4 women in here, so it's happening. But yeah, we study noble gases in lunar samples. So for anyone who can't remember, it's okay, I don't know. We have a periodic table. Yeah, the last column over there. So we look at neon, argon, krypton, and xenon. At the moment, we're mainly looking at argon. So we look at something we basically do argon dating, which is kind of like carbon dating, but we're using potassium as it decays to argon over like 3 billion years or something like that. So, carbon dating is great for terrestrial rocks that are a few, 1,000 years old or whatnot. We use it for samples that are billions of years old. So much older, basically, watch in the sample. So we're kind of like rock detectives. Pretty much, we take our rock from the moon or Mars or asteroids or whatnot, and we put it into this system here. So we take these really precious samples from Apollo and we destroy them. It's all for science, so it's fine. You guys can come around this side as well. So there are a bunch of samples already in here. This is our sample chamber. You can't see the samples, they're wrapped up in foil. But this is where we load those samples into, and then we use the laser here to destroy those samples. So, I think my job is like, pew, 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 but it makes no noise, like absolutely no noise. So I wish it did, but it doesn't. We are actually putting a new software in, so when we fire the laser, we're going to try and get it to make it, yeah, exactly. You gotta have some fun, right? So yeah, this is the way we get the gas out of the sample. So argon's a gas. We're trying to get that argon that's trapped in the sample and built up over time, released from the sample. So once we heat it up with the laser, blast it with the laser, it releases that sample. It releases that gas even. And it comes into what we call our preparation area here. So in these tubes is where the gas will flow. And just to give you an idea, we have to remove everything that's out of the inside, every type of gas that's inside the tube before we start analysing, because there's more argon in one of your breaths than there is in most of our samples. So, imagine how much argon is in the atmosphere. That goes, when you're building these things, all that atmosphere gets trapped in there, so you're trying to remove it. So we have these big loud things, which are called pumps. They're underneath the table and stuff. They basically make the inside of the system a vacuum. So it's not quite as good as the vacuum of space, but it's not far off it. So we're trying to get rid of everything. There's still bits of argon, so we measure blank levels. But yeah, we let the argon flow. Then we have this magical thing here. It's called a source. And it's called a source. So that's basically shoots a beam of electrons at the gas, and it gives them a charge. So because they have a charge and they have different weights, because we're looking at different atoms with different weights, so we're looking at different isotopes. Sometimes I give this story to kids of 5, so the isotopes are what? So yeah, once they have a charge, we can manipulate them in this big thing here, which is our magnet. So you can imagine throwing a feather, throwing a bowling ball in the same direction. The heavier one's going to get deflected less by the magnetic field of the feather, right? Same with isotopes. The lighter ones get manipulated a lot more. Then we have detectors down at the other end that collect all this information. And this guy does all the hard work. We just sit at the table there and watch the scan come through. But yeah, that is how we measure the sample. And I mentioned we're looking at argon. So we're looking at how much argon is in that sample to get. Our main aim is to get an age of the sample. So I said we're rock detectives. We want to know what the sample's made up of and how old it was. So for the moon, that's generally older than 3 billion years. Some of the rocks are older than 4 billion years. Now, why is that important? Because lunar samples are great, because we have a great history here on the Earth, but because of plate tectonics and wind erosion, water erosion, some of that evidence has been removed from the surface. So the moon kind of is like textbook. We got Earth, which is textbook 2. The moon is kind of like textbook 1. You can learn about that early solar system history from the surface of the moon. It's got these ancient surfaces. And I do have some samples to show you as well. Sorry. This one's a giant paperweight at the moment, but we are, so just the magnet on the other side is actually probably the equivalent of a baby elephant. It's like 3/4 of its one. So we would love to send these instruments into space and like do like of course because like they've got better vacuums than us as well. But if we asked any payload expert, can we send a baby elephant into space, they'd probably tell us no. So we are working to make these instruments smaller. So behind the black curtain, it's usually open, which sucks, but there is a smaller version of this instrument without the magnet. It uses a slightly not as sensitive instrument, so you don't get as good ages, but you still get really good ages, but it's not as good as this.
It's a good compromise.
It's a good compromise, yeah, exactly. So if you want to send something onto a rover, and the little guy over there as well, that is also going to be like we're developing that to hopefully go on a rover or go with astronauts to the surface, so they can actually, take ages as they go, because realistically, we want every sample from everywhere, bring it back so we can date it, but people keep telling me no for that one as well, so so yeah, we need to take like rovers or something in a great, or like sending these instruments to space would be fantastic. So I do have a lunar sample that you can touch, courtesy of Stacy. I think you might have met Stacy already. Not yet, but you will soon. So I've got gloves on at the moment, but you guys can touch it. I always touch it to make sure it's real, but yeah, feel free to pass it around. Take pictures and whatnot. That is a lunar meteorite, yeah. So unlike the Apollo samples, which were a bit lazy and took a rocket here, these guys had a very tough journey to be ejected from the surface of the moon during an impact event, so like an asteroid or comet hit the moon, sent material flying into space, and it eventually lands here on Earth. So this one was found in Northwest Africa, but we get ones found in Antarctica. So the first picture over there, my boss has been to Antarctica 4 times to look for lunar meteorites, and she took that picture. I took the other 3. I wish.
So how do we find if this meteorite came from moon?
Good question. So you can kind of imagine that every rock is kind of a person. It has its own personality, it has its own characteristics, and it has its own fingerprint. So we have Apollo samples that directly compare the lunar meteorites to, because we know the chemistry of the Apollo samples, we know it's slightly different to the moon, to the Earth, sorry. So we can kind of compare the two. Yeah. We also, like for Mars, we don't have that. So we don't have any samples returned from Mars. So how do we know
if
like what fingerprint Mars has?
Yes.
But we do have orbital data that comes from Mars. We have rovers, Mars Curiosity rover. It's currently roving around, firing like drill holes everywhere. And that's taking element data as well. So now we're 100% sure things like this guy, sorry it's so small, but came a long way. This is from Mars.
Oh wow.
Yeah. So we have a little piece of Mars there as well.
Yeah. Do you? I was at an event at ASU.
Okay.
Their Mars facility,
Yeah.
and
My family is dancing here. My wife said to kiss the rocks. Look at that, Preeti. This would have been a beach environment. And he got umbrella, I got a trash cover. This is definitely a wow place. Everybody's saying wow. This is the first of the kind in our lifetime. I mean, damn.